Section 15 is called the Fundamental Theorem of Algebra. It's going to finish up our discussion on polynomials before moving on to a new type of function. And the first topic in the Fundamental Theorem of Algebra section is on linear factorization. Now, linear factorization requires the Fundamental Theorem of Algebra to guarantee that it is possible to create a linear factorization. So let's see what the fundamental theorem says. It says that every polynomial function, now that's a pretty powerful beginning statement. It says every, that means any polynomial that we can create. Now that means we have to understand what the definition for a polynomial function is. And it says every polynomial function of degree 1 or higher has at least one complex zero. So I want to look at a couple of examples of polynomial functions and how this particular theorem might apply. So for example, if I was to look at the equation f of x equals 42, that is a polynomial function. It's a very basic polynomial function, and if I was to calculate the zeros for this by letting f of x equal to 0, then I would end up with the statement 0 equals 42, and that would most certainly be false, which means there are no zeros. But this is saying that every polynomial has at least one complex zero. Did we miss it? Or did we incorrectly use the theorem? So look closer at the equation f of x equals 42. This is a constant function. Constant function has degree equal to 0. And this theorem only applies if your polynomial function is of degree 1 or greater. So this is exactly what we should expect. We are not supposed to have at least one complex zero with this because it doesn't have a degree 1 or higher to it. So let's look at another example. Let's say we look at the equation f of x equals 2x minus 3. And if I was to try to calculate the zeros for that, let f of x equals 0, then I would end up with the statement 0 equals 2x minus 3, which would eventually lead me to x equals 3 halves. Now, with x equaling 3 halves, I do have at least one zero, but it says that we're supposed to have at least one complex zero. So you're going to need to go back and refer to our conversations about complex zeros and really the complex set. In other words, what does this symbol double bar C really mean? And when we discussed it prior, we had said that this is the set of all complex numbers. And this includes all real numbers, and it also includes just the regular imaginary numbers. So x equals 3 over 2 may not have any i's in it to make it look like an imaginary number, making it complex, but if we allow ourselves to think of the word complex here as really meaning the entire complex set, then any real number would also fit into the category of being complex. So these are two examples. One of them does not work because it's not going to fit the condition of having degree 1 or higher, but the second example is certainly a linear function, which is a degree 1, and with degree of 1 higher, we're supposed to have one complex zero, and we do. And the next theorem, which might be the one that's most beneficial for us, which is why I've named part 1 of this section 15 the linear factorization. The linear factorization theorem says that if f of x is the equation of a polynomial function of degree n greater than or equal to 1. So the reason why this theorem starts with that statement is because then any of the consequences from the fundamental theorem of algebra would also apply. So you have to have the fundamental theorem of algebra in order for this next theorem to exist. And it says if this happens, then you will be able to have an A as well as a C1 through Cn coming from the complex number set where A is not allowed to be 0, such that the following can be done. And what we have right here is a factored form of the polynomial. And if you look closely at each one of the factors, every single one of these factors has a power of 1 on the x, which means that each factor is linear. Hence why we call this the linear factorization theorem. Now back to the A and the C1 through Cn. What are those things? Well, A is going to represent the leading coefficient of your polynomial. So whatever the leading coefficient is of the polynomial when it's in standard form, that is also the leading coefficient whenever it's in factored form. For C1 through Cn, these represent the zeros of f. So if you can calculate all the zeros of f, which would be the real ones and the complex ones, the imaginary ones, then you can put those into this factored form called the linear factorization, and it will automatically give you the factored form for your polynomial. So we'll be seeing the linear factorization theorem used in two different ways. We'll have two different sets of examples in this section.